Hello and welcome to this video lesson on amines and amides, two products that are very useful in industry, for example your shampoos and your fabric softeners, two products made from ammonia. Okay, so we're going to deal with these in a little bit more detail now. And by the way, the specification reference is 3.4.4 and also 3.4.7. So this is what we're going to do in this lesson. First of all, we're going to apply our UPAC rules. So that's the International Union of Pure and Applied Chemistry, and they make up rules for naming all organic compounds, and so we're going to use those rules to name a bunch of amines and amides, so that you'll be able to name any amine or amide that you come across. That's number one. Number two, we're going to know that quaternary ammonium salts, so we'll have to know what they are to start with, and then once we know that, we'll be able to understand that they can be used as cationic surfactants, so we'll have to learn about what they are too. They're quite useful. And lastly, we will explain the difference in base strength, so how basic, how alkali that is, all the different amines are. So from ammonia, comparing to ammonia, all the different amines, how strong a base are they compared to ammonia? And we'll be able to explain the differences as well. Okay, so that's what we're going to do. Should we crack on? First of all, let's have a think about what are amines. Well, amines start from ammonia. So if we start with ammonia and then replace one of the hydrogens with an organic group. Then we'll get an amine. Okay, so that's what we are. Let's draw ammonia to start with then, shall we? So ammonia, as you'll know, is nitrogen surrounded by three hydrogens. So as we've said, so let's just label this ammonia first, shall we? That's ammonia. And so if we do what we've said at the top there, replace one of the hydrogens with an organic group. So these two at the bottom we're going to leave alone, but if the one at the top we replace, and let's call that the organic group R. Okay, so we're going to call that R. So we've replaced one of the hydrogens with an organic group that we've named R. Could be, nearly any organic group. And if we do that with just one of the hydrogens, then what we get is a primary amine. Okay, and we can do it again. Okay, we can leave one of the hydrogens alone, and we can leave that particular organic group, alkyl group usually, alone. But if we replace another of the hydrogens with another organic group, usually an alkyl group, then because we've got two alkyl groups, we're going to call this a secondary amine. And guess what? We can do it a third time. Okay, so we've still got a nitrogen in the middle, but now we've replaced all three hydrogens with alkyl groups, or well, I should say organic groups really. And if we do that for all three of the hydrogens, then we're going to call that a tertiary amine. A tertiary amine. Right, but it doesn't stop there, as it happens. Even though we've used up all our hydrogens, there is one more step we can go through. Is you can actually form ions. they're called quaternary ammonium ions, because what happens is you get an extra organic group. So you've got 4 altogether, 4 extra organic groups, but the nitrogen atom in the middle becomes charged, so it's an ion, and they are called, this is because there's 4 of the organic groups, quaternary ammonium ion. Okay. And because these quaternary ammonium ions are positive, if there happen to be any negative ions around, they would be attracted, and they can form salts, and those salts might be called quaternary ammonium salts. And so we're going to look at those in a little bit more detail later. But the last thing to say is that amines often smell quite fishy with the small amines, and if it's small it just means there's not much to the organic group. There might be 1 or 2 carbons in the organic groups, but and they smell slightly fishy. And then the amines with larger organic groups, the larger amines, they smell more fishy, very fishy. Not an entirely pleasant smell, but nevertheless. So now we know what an amine is, we can go through the process of naming amines. And it's not too difficult, it's quite similar to the other organic naming that you've been doing. And so what we can say to start with is that the suffix, the bit at the end of the name, is going to be amine. Okay, and the prefix is going to be the organic group, or is going to at least going to depend on the organic group. Okay, so I think the easiest way to do it is to do it with a few examples. So let's draw one here. Let's draw an amine. Let's draw an amine. We've got, of course, got a nitrogen. We've got a hydrogen. We've got a hydrogen, and our organic group. Let's give it CH2, CH2, CH3. Okay, so let's name this. Well, our suffix, as we've said, is amine, because it's an amine, and we can tell that because it's got this NH2 group, and our organic group has 3 carbons on it. 1, 2, 3. So that means we're going to call that propyl amine. Okay, so I just write the suffix propyl amine, all in one word. So that's how we name this particular amine. Let's try a different example. Get slightly more complicated. So again, we've got a nitrogen and a hydrogen, but let's say we've got two organic groups with a CH2 and a CH3 off one of the nitrogen bonds, and another CH2, CH3 off the other nitrogen. So it's still an amine, so we'll write our suffix in. It's still an amine, but what are we going to call it? Well, in each of these groups there are 2 carbons, so that would normally be ethyl amine if it was just one of them, but because there are 2 of them, there's one here and there's the second one there, we're going to say diethyl. So diethylamine. Okay, that's our second example. Let's do another one. So again, let's have a nitrogen in the middle and methyl at the top. In fact, let's have 3 methyls, shall we? Okay, so in the same way, we're going to call it an amine. Alright, because it's a nitrogen with 3 things off it. But now we have 3 alkyl groups, and they're all methyls. Okay, they're methyls because we have 1 carbon in each of them. So that's going to be tri, because there are 3 of them, methyl, because there are 1 carbon, there's 1 carbon in each. Okay, so we're going to write tri-methylamine for that one. Okay, we'll do one more. Let's do a quaternary ion now, so we can try and fit it in down here. So again, we've got the nitrogen, and it's an ion, so that's a positive charge. So let's say we've got methyls hanging off. We're going to have 4 methyls hanging off them. Okay, so of course we're going to have the suffix being amine again, but what's the prefix going to be? Well, it's an ion, so we're going to say amine ion. So each of these groups have got 1 carbon in them, and there are 4 of them, and the the code for 4 is tetra, so it's going to be tetra methyl amine ion. Tetra methyl amine ion for that one. Now we could do one that is slightly more difficult, where we have 2 different organic groups. Let's do one with different organic groups. Maybe I can squeeze it in on the left hand side here. Okay, so we've got our nitrogen in the middle as usual, and as it happens, an exam paper might not be quite as kind to you as these examples with nitrogens in the middle, leading you to suppose that it's an amine straight away. It might be written out a bit more horizontally than this. But nevertheless, let's draw this amine here with 2 different alkyl groups hanging off the nitrogen. So we'll have a methyl group hanging off the top of there, and let's have a propyl group hanging off here. So propyl is 3, so we've got CH2, CH2, CH3, and we just have a hydrogen coming off that side there. Okay, so let's do this. We're going to have to count them separately this time. So 1, 2, 3 carbons on this one, so that's going to be propyl. I'll write a little propyl up here. 1 carbon here, so that's going to be methyl. Okay, so which one do we write first though? Obviously our suffix is going to be amine. But do we write methyl propyl amine, or do we write propyl methyl amine? Well, what we do is we write them in alphabetical order. So we compare the M to the P, and we know that M comes before P, and so we write methyl propyl amine. Methyl propyl amine. All one word, even though I've left a little space there between methyl propyl and amine. Okay, that's about it for naming amines. I think I've given you a few different options there, which should cover all examples you might get in an exam. Okay, we're going to move on now to cationic surfactants. After we've just checked what learning objectives we've done. Okay, so have we, for example, applied IUPAC rules for naming amines and amides? Well, we've done amines, but we haven't done amides yet, so I'll put my tick there. Do we now know that quaternary ammonium salts can be used as cationic surfactants? Well, not yet. That's what we'll do next, shall we? Okay. So first let's unpick these two words, cationic and surfactants. Well, surfactants, let's just define surfactants as a compound is partly soluble and partly insoluble in water. It's sort of like emulsifiers were in GCSE. Okay, so that's what a surfactant is. It's a compound that is that part of it is going to be soluble and the other end of it is going to be insoluble in a polar compound such as water. And you'll remember also from GCSE that cationic is a positive ion. All right, so it's our polar part of the surfactant is going to be a positive ion. So let's draw one out as best we can, at least. What we're going to draw is a quaternary ammonium salt with one of the alkyl groups being a very long chain of hydrocarbon. Okay, so it's a quaternary ammonium salt, so we're going to have a nitrogen with a positive charge in the middle, and that's going to be bonded to methyl group, say, another methyl group, and another methyl group. Okay, so it's got four bonds to it, because that's what makes it quaternary. But as we said, one of them needs to be a very long hydrocarbon chain. All right, so let's draw the long hydrocarbon chain like this. You'll often see this. Okay, so each of these corners is supposed to represent a carbon atom, because in reality the hydrocarbon chains are not long and straight like you see in the displayed formula. The bond angles are disjointed like we've drawn here. Okay, so let's just label it. So this is our long hydrocarbon chain. That's our long hydrocarbon chain, and it is insoluble in water. And so this group here, means all of that end there is our positively charged group, let's call it, and this is soluble in water. Okay, so that's the quaternary ammonium salt, at least the positive ion of the salt, and it's the explanation of why one end of it is soluble in a polar compound like water, because the nitrogen has a positive charge to it, and why one end is not soluble in water, because the long hydrocarbon chain is not charged in any way. Okay, so first let's unpick these two words, cationic and surfactants. Well, surfactants, let's just define surfactants as a compound is partly soluble and partly insoluble in water. It's sort of like emulsifiers were in GCSE. Okay, so that's what a surfactant is. It's a compound that is that part of it is going to be soluble and the other end of it is going to be insoluble in a polar compound such as water. And you'll remember also from GCSE that cationic is a positive ion. All right, so it's our polar part of the surfactant is going to be a positive ion. So let's draw one out as best we can, at least. What we're going to draw is a quaternary ammonium salt with one of the alkyl groups being a very long chain of hydrocarbon. Okay, so it's a quaternary ammonium salt, so we're going to have a nitrogen with a positive charge in the middle, and that's going to be bonded to methyl group, say, another methyl group, and another methyl group. Okay, so it's got 4 bonds to it, because that's what makes it quaternary. But as we said, one of them needs to be a very long hydrocarbon chain. All right, so let's draw the long hydrocarbon chain like this. You'll often see this. Okay, so each of these corners is supposed to represent a carbon atom, because in reality the hydrocarbon chains are not long and straight like you see in the displayed formula. The bond angles are disjointed like we've drawn here. Okay, so let's just label it. So this is our long hydrocarbon chain. That's our long hydrocarbon chain, and it is insoluble in water. And so this group here, means that all of that end there is our positively charged group, let's call it, and this is soluble in water. Okay, so that's the quaternary ammonium salt, at least the positive ion of the salt, and it's the explanation of why one end of it is soluble in a polar compound like water, because the nitrogen has a positive charge to it, and why one end is not soluble in water, because the long hydrocarbon chain is not charged in any way. After we've just checked our learning objectives. So as before, we checked that we've named amines but not amides, and now we know that quaternary ammonium salts can be used as cationic surfactants in fabric conditioners and hair products. So we've done this one. So let's move on now, still with amines, but we're going to explain the difference in base strength between different types of amines, i.e. ammonia, primary aliphatic amines, and primary aromatic amines. And in order to do that, we're going to see how amines form dative covalent bonds, or also known as coordinate bonds. So let's draw ourselves an amine. Okay, we're going to do a primary amine. So we're going to start with our nitrogen. We'll have just a single alkyl group that we'll call R. So it's primary, so we've got the other 2 as hydrogens. And as you'll remember, or you could quickly check from a periodic table, nitrogen is in group 5 of the periodic table, which means it's got 5 electrons in its outer shell, 3 of which are occupied in these 3 bonds that we've already drawn. Okay, so that leaves it still got another 2, and those 2 will be a lone pair of bonds. So let's draw the lone pair like this. So they have a lone pair of electrons, and that's quite a dense area of negative charge. A lone pair is because they're not being drawn off to another nucleus as the bonding electrons are. So they're quite densely negative, and so they're going to be on the hunt for any positive charge that might be around. So say you had a hydrogen ion in the vicinity, then what would happen is we draw it as a curly arrow, the lone pair would be attracted to the hydrogen ion. And so what we see here is the amines acting as Bronsted-Lowry bases because they're accepting a proton. And very much later on in A level you will come across Lewis acids, and the definition of a Lewis acid is that they're donating their lone pair. So in either way, Bronsted-Lowry or Lewis, you can see that they're acting as bases. So when this lone pair has accepted the hydrogen, we're going to draw it like this. So still got our hydrogen there on the left, still got our nitrogen, still got our alkyl group, still got our other hydrogen. But now we have a bond with this hydrogen that was a proton. But it's been to just distinguish this new bond from the normal covalent bonds that we have, the three normal covalent bonds that we had. We draw it as an arrow like that, like you might have done in the section in bonding. Okay, so that signifies the dative covalent bond. But of course, let's not forget the positive charge of the proton, of the hydrogen ion, that we still have. But that's drawn like this. All right, so we just draw it around in a set of square brackets and write the positive up there, because the electric charge is distributed evenly, and that's why we draw it with the square brackets and the positive charge outside everything. So let's summarize that in words, and so we can say that amines act as Bronsted-Lowry bases because they accept protons. Okay, but here's the thing. How inclined is an amine to accept a proton? Well, the answer is, how available is this lone pair? All right, so if I just take a new color, let's take, so this lone pair here, and I'll pose a question: how available is it? Okay, how available is it? Well, it varies. How available is that lone pair, which is present in all amines? How available it is, it depends on the other groups that are attached to the nitrogen. So let's, and if the lone pair is very available, there's going to be a high density of negative charge there, then that's going to make it very basic. It's going to be more likely to accept a proton. But if that charge that is in the lone pair is less available, because it might have been, sucked into the rest of the molecule, if it is less available, then it's going to be less basic. Okay, so what you need to know is you need to know which amines are more basic and which amines are less basic. So we can use ammonia as a yardstick, and why the lone pairs are more or less available in each case. So let's do that next. Okay, here in this slide we're going to look at the difference in base strength between ammonia, primary aliphatic and primary aromatic amines. So the three of those amines, we're going to compare their base strengths. Let's start off with an aromatic amine, and here I've drawn you one. So again, we've got our nitrogen with our lone pair, This time it's a primary aromatic amine, so we've got one benzene ring of the nitrogen and two hydrogens of the nitrogen, and importantly we've got the lone pair being available on the nitrogen. And you remember from the last slide that we said that the basicity depends on the availability of this lone pair. But what happens with aromatic amines is that the benzene ring is quite electronegative, and so it draws electric charge, a negative charge, away from the nitrogen in towards itself. So let's represent the negative charge associated with electron density by some green highlighter like I've illustrated there. And so what you're going to see is that for these aromatic amines, the electric charge is drawn in this direction via that bond towards the benzene ring, so that we can represent it such as this. Okay, so what that means is that these, out of the three types of amines, ammonia, aliphatic and aromatic amines, this is going to be the weakest base, because that lone pair is less available. There's less electron density out on the outside of that nitrogen atom because it's been drawn towards the benzene ring. Okay, let's have a look at next at ammonia itself, and again we've got the nitrogen in the middle with the lone pair, and just three hydrogens hanging off the nitrogen. And so in this case we can see that the electron density is pretty much centered around the nitrogen, which is quite an electronegative atom, but it's not being drawn one way or the other by the hydrogen atoms. So then what we can do is, so that's going to be a more available lone pair than in the aromatic amine on the left. Whereas an aliphatic amine, like we've drawn here, so that's an amine with an alkyl group represented here as R. What happens with the aliphatic amines is that the nitrogen is more electronegative than the alkyl group that's summarized as R there. So what happens is the electrons are drawn away from the alkyl group towards the nitrogen, such that the electric charge and the electron density is very much focused outside the nitrogen atom. So the lone pair is very available. And because that lone pair is so available, then we can clearly see that these types of amines, the primary aliphatic amines, are going to be the strongest bases. And so that's the trend from aromatic, weakest base, through neutral, which is ammonia, through to the strongest bases, which are the aliphatic bases, because the electron density has been pushed towards the outside of the nitrogen atom, making that lone pair very available to any protons that might be swimming around nearby. Okay, let's just check where we are in this video lesson. We of course named amines earlier, and we looked at fabric conditioners and hair conditioners as cationic surfactants, and we've just explained the difference in base strength between the different types of amines. So we've done that. The only thing we've not done is we've not done naming and understanding amides. So let's do that next. So amides are related to amines, but have different chemistry. And let's have a look at the structure of an amide to understand why they behave differently. So it's centered around a carbon atom again, and we have a double bond with an oxygen and an alkyl group, and the NH2 group comes off the carbon, something like that. So that's the functional group, and let's just split the functional group into its two individual functional groups. So this is called the carbonyl group, And of course we've got our NH2 group here as well. And together they form an amide. What happens to make the chemistry different from amines is that the electrons get drawn away from the NH2 group by the carbonyl group, and that means that the lone pair that is hanging off the nitrogen is less available, and so the chemistry is different. So let's summarize that by saying the electrons, or the electric charge to be better chemistry wise, they are drawn towards the carbonyl group. So that's what an amide is, and there's a little trick that helps you remember the difference between an amide and an amine, and it's this. So if we write down amide, right, we've got a D in amide, and that could stand for a double bond, whereas in an amine we have an N in the amine, and that could stand for no double bond. And here's the double bond that we're talking about, of course. And that's how you might remember the difference between an amide and an amine. Okay, so that's what amides are. What we'll look at now is how to name them. Okay, naming amides is fairly easy. What we do is we start off with the alkyl group, some sort of derivation of the alkyl group. So like methane, etc. And then we finish off with amide and make it all into one word. So let's have a look at some examples. Simple one first. So you'll see that you'll recognize the functional group to start with. So we know it's, if you look at this bit here, we know it's an amide from that bit. And now, so the second part of the word is going to be amide. The first word is going to come from, the first part of the word rather, is going to come from the number of carbons. So we've just got one carbon in this, so it's going to be methane. So it's going to be methanamide, all as one word. And we just drop the E of methane from the fact that it's one carbon in the amide. So we drop the E of methane, so it becomes methanamide. Okay, so now we notice the same functional group, which tells us that it's an amide. So let's write amide, the easy bit. And then what we do is we're going to count the number of carbons, 1, 2. And so then you'll know from the list of carbon. So if it's one carbon, it's something to do with meth, and then it's eth for 2, and prop for 3, and but for 4, etc. Okay, so this is 2 carbon, so it's going to be ethanamide. That's all one word. Ethanamide for that one. This last one is slightly more difficult because we've got a methyl group coming off the main carbon chain, but at least we can get the back end of the name. So of course it's going to be amide because we spot that functional group. And now what we do is we're going to count the number of carbons. So we've got 1, 2, 3. So it's going to be something to do with prop. but we've also got this carbon here, this methyl group here. So let's just highlight that in a different color. We've also got a methyl group here. So we've got a choice here. Let's in red. Let's put our choices here. So we've got a choice of methyl and something to do with prop. Which one are we going to write first? That's the question. Well, M becomes before P in the alphabet, so it's going to be methyl. Propan amide, all as one word, is the name of the third one. And so you might get asked in the exam to name something like that third one, but you're unlikely to get asked for one any much more difficult than that. But in any case, you follow the same procedure and you'll get it right. So now what we're going to do is we're going to look at a little derivation of amides, and they're called N-substituted amides. And an N-substituted amide is just where one of the hydrogens that's hanging off the nitrogen is substituted by an alkyl group. So let's draw one here. So we draw a normal amide. So let's start off with a nitrogen, hydrogen, hydrogen, carbon, double bond oxygen. Let's put a couple of carbons over here. So if we named this one, we'd first of all recognize the fact that it's an amide from the functional group, and then we'd count the carbons. So we know it's an amide, so we could write amide in, and then we count 3 carbons, so that's going to be propanamide. So it would be propanamide, and when we get an N-substitute amide, one of these hydrogens that's hanging off the nitrogen is substituted. So let's go blue and substitute this hydrogen for a methyl group. And so that bond now is like this from the nitrogen straight onto the carbon. And instead of the nitrogen being bonded to a hydrogen, it's now bonded to a methyl group. And how we would name this one is we would use a capital N because it's a nucleophilic substitution. So it's N, and then we need to name the group that's been substituted in. So this is methyl, and it's propanamide. So instead of just propanamide, we have to say N-methyl propanamide. Let's do another example, just to be thorough. So let's start with our functional group again. Make it a bit shorter. So normally we would have a second hydrogen coming off the nitrogen, but in this case, let's make our substituted group C2H5. So the name of this is going to be, it's got 2 carbons on it, so it's going to be ethan or ethyl. So that's the ethyl group that's been substituted in instead of the hydrogen, and that's for the nuclear substituted in bit, but for the original bit of amide we need to count these carbons, and we've got 2, and so from the 2 we would get or ethan again from the 2 carbons. So then we would name it as N, and we'd start with the group that's been substituted in. So ethyl, ethan, amide. Hopefully you see where that's come from. So we've got 3 groups. Let's use a green. We've got 1, 2, 3 groups. So that of course comes from the functional group. And this comes from the main alkyl group. And our first bit comes from the group that's been substituted in. There, hopefully you can see how we name not only normal amides but also N-substituted amides. And lastly, just to finish off this video lesson, let's just check we've done all our learning objectives. Well, of course, we've already checked that we've named amines, and now we've also checked amides. Right, so we can now name both. And as far as amides are concerned, that's about it. As all that you need to know about amides is to recognize them from the functional group and be able to name them. And the subject of one of your organic chemistry lessons will be how to make amides, but that's not the subject of this lesson. Okay, so our second learning objectives was that quaternary ammonium salts can be used as cationic surfactants. We've done that, shampoos and things. And we also explained the difference in base strength, which all came from the availability of the lone pair, which was affected by the electronegativity of whatever group is attached to the nitrogen. Good, we're all done. I hope that's been clear.